Wallace test, which we'll talk about today. Last time we talked about ANOVA, but this time we're going to include different size groups, J1 up to Ji. So it's just small changes for SST now. In the formula for SST, instead of J, we'll have J sub I. And the degrees of freedom, instead of I, J minus 1, will be the sum of the Ji's minus 1. SSW, instead of J, will have J sub I. And the degrees of freedom, instead of I times J minus 1, will be the sum of Ji minus 1 parenthesis. And for SSB, again, instead of J, we'll have Ji, and the degrees of freedom won't change. So our F test now, with degrees of freedom or parameters I minus 1 and the sum of Ji minus 1 parentheses, will be SSB over I minus 1, SSW over the sum of the Ji minus 1 close parenthesis. So now, if we reject the null for ANOVA, we don't know which of the treatments is having an effect on the mean, and you may wish to do pairwise t-tests. However, if you did each of them at level alpha, then having I choose 2 simultaneous t-tests, each at level alpha would have an overall type 1 error of I choose 2 times alpha, which is way too big. So what we do is we reduce the size, we reduce the significance level for each of the tests to alpha over I choose 2. The problem with this, however, is that because the significance level is so small, it's actually difficult to detect, to reject the null for these t-tests. So you may not, even though you reject the null for ANOVA, you may not actually be able to reject any of the nulls for these simultaneous t-tests. Another problem is that you have to do I choose 2 of these t-tests, which is really quite burdensome. So in part because I can't really test you on doing I choose 2 t-tests, we're going to actually do a shortcut Bonferroni, which is, you sometimes see this done in the literature, but we'll do it here again just because it's something I can test you on. But most likely, if you were publishing, you would want to do a full-on Bonferroni. We'll also talk about the Kruskal-Wallis test, and I'll at least give you the R code for how to do it in R. So the shortcut Bonferroni is what we're going to do. Instead of doing I choose 2 simultaneous t-tests, we're going to make I 101 minus alpha over I confidence intervals, and just I them. So for each group, we're going to get a confidence interval for the true. We're going to get a confidence interval for the mean, and we'll just I essentially whether these intervals overlap or not. If they don't overlap, it's very unlikely that they have the same mean. So in that case, we would say they have different means. So I should remark that doing the shortcut Bonferroni method is a little awkward. It's hard to make precise what I mean by it's unlikely that the two treatment means are the same. It's much more precise when we do pairwise t-tests, but again, I think it's clear that if you are looking at these intervals and two intervals aren't overlapping, then it's very unlikely that they would have the same mean. So let's just do an example. In our three-group example, we ended up rejecting the null. We perform a shortcut Bonferroni, and so our 101 minus alpha over I confidence interval is what's shown here, and so we have the row mean plus or minus the cutoff with the degree. So it's the cutoff given by the quantile for the t distribution with ji minus 1 degrees of freedom for probability alpha over 2I. And then SI is the within group sample SD for group I divided by the square root of JI. So this formula should make 100% sense to you. Make sure you understand every part of this. In our example, we had the SI for every group is 1. You can see so the sample variance for row A is 1, and the sample variance for row 2 is also 1, and the sample variance for row 3 or C is also 1. So if we so to calculate these cutoffs, we have a special Bonferroni table. So this is not in the book, but I'll provide it for you. So here, the 2 is the degrees of freedom, and the 3 is the number of tests that we have. And of course, here we're talking about 0.025 divided by k as the probability. So we get 7.648, and hence it's 2 plus or minus 4.41, 4 plus or minus 4.41, 6 plus or minus 4.41. And if you plot these, you see that they don't overlap, and hence we would not be able to conclude that the means, the group means, any of the group means are different from one another. And again, the reason for this is because alpha over I level of significance is making the confidence intervals too large. To solve this problem, you would need to have a larger number of observations. Notice here in this formula for the confidence interval, if you have the ji's being larger, it's in the denominator. It's SI over square root of ji. If ji is larger, that would make the intervals shorter. So there's really no conclusion that we can make from shortcut Bonferroni here. So now, to show you how this works in R, I just made a stupid example of 3 treatment groups, 12 numbers from 1 to 12, and I just plotted them. They look relatively normal. I did some tidying up of the data so I can make box plots, and you can see the variance doesn't really look uniform, doesn't look the same here, but we'll ignore that. And we did an F test, so the means are 3, 7.5, and 11. The variances are different. I compute SSW, SSB just from the formulas, hence I compute the F statistic, which is 33. That's pretty large, so it has a small p-value. So I would reject the null. You can automate this using one-way.test, and notice that you get the same answer. If you set the option for variance dot equal true, if variance dot equal is false, then that sort of treats the case when variances aren't equal. And I'm not exactly sure how R is doing this computation, but you can see that the p-value isn't as big, and so you would have less chance of rejecting the null, it looks like here. But probably it would be the appropriate test to use here. Otherwise, you could do a non-parametric test. So the shortcut Bonferroni method, here I computed all of the endpoints of the intervals. So for T1, T2, and T3, I didn't plot this, but if you look at these intervals, I'll highlight them at least. So here's one, here's the other, and here's the third. You'll see that T1 and T3 intervals are not overlapping, so we would conclude that those means are different. Now the Kruskal-Wallis test is a non-parametric test. It's a generalization of the Mann-Whitney test to two or more treatment groups. And so here Rij is the rank of Yij in the combined sample. Ri dot would be the average rank of the ith treatment group, and R bar dot dot would be the total average. And with just a little bit of algebra, you can see that this is n plus 1 over 2. We define SSB just how we did before, except now we use ranks, and we have this formula here. And this is a measure of the spread of the row rank around the total rank. And if the null is true, that each treatment group has the same distribution, then SSB should be small. So now, as before, SSB over the variance of a rank is a chi-squared with I minus 1 degrees of freedom. So here, what I mean by the variance of a rank is Rij. So from my sample, like if I just take a rank, so let's say a number from 1 to 12, what's the variance that I get when I just randomly choose a rank? So that's something that you can compute at least approximately for a sample at least, right? So if your total sample size is capital N, you can show very easily that the sample variance is n times n plus 1 over 12. So we'll approximate that for the variance of the rank, and so our Kruskal-Wallis TS is defined as SSB over n plus 1 over 12. And this is a chi-squared I minus 1. If the null is true, we expect a small number, otherwise we would reject. So that is it, and I've provided you with some R code to see how this is used. This is very straightforward. I'll just mention here I just hard-coded all the computations that we just did above, and I just show you that there is a built-in Kruskal .test that you can use to automate this process. You just have your treatment vector and your group vector, and that's it. And so we get the result that we would reject the null, that the three distributions are the same. Okay, have a great day. I'll see you next time.